the lights. Let's say if I turn the lights off, it will be off. So what is a clock signal? So this D will not get the value of Q immediately, right? We need to generate a clock. Like, it's not toggling every time. Like, if I push it, you saw it didn't toggle. There are two main reasons of this. Bouncing the button is one of the most important logics. Many beginners get confused when these kind of things happen. Hello everyone, welcome to day 14 of the 100-day FPGA series. In this video, we are going to be starting sequential circuits. So till now, from day 1 to day 13, we have covered a lots of combinational circuits, okay? So I have shown you a lots of different techniques and lots of different circuits, combinational circuits, through which you can do any combination problem. So whenever you are thinking about combinational circuits, you can watch those videos, you can learn from them, and you can actually build more or less all sort of combinational circuits from the knowledge that we have gained from day 1 to day 13. Now, starting off in the sequential circuits is one of the most important things that we are going to be learning, since in larger designs it's not combinational usually. Usually a lot of sequential elements are required in designing real world problems. Let's get into sequential circuits. So if you see the textbook definition of sequential circuits, you will see that the sequential circuits are those circuits that depend not only on the present input but also on the previous inputs as well, okay, previous states. What that statement is saying is basically a certain metric of time is involved, okay? So if you see any sort of combinational circuits that we have studied, like encoder, decoder, and mux, and whatever the gray converter and everything that we have studied from day 1 to day 13, they all do not have an element of time in it, because you give the input. Even in the FPGA, you saw I demonstrated those stuff on the FPGA, and we flicked the switches and we got the outputs on the LEDs. We didn't have to wait, right, in any sense, and the element of time was not there. So in sequential circuits, the element of time will be there, because in real world systems, all the circuits are not combinational, okay? So some circuits are combinational. If you see the lights, let's say if I turn the lights off, it will be off, right? If I turn the lights on, it will again be on. So this is combinational. Here I am flicking the switch. The output is related to the present input and not on the past output. It's not depending upon what the previous inputs were, okay? So basically the time is not involved in such circuits, in combinational circuits. But in sequential circuits, you have the time involvement. Let's say you have a light that turns on and off every second, okay? Something like a blink circuit. So there you need to measure time, right? So in those circuits, those kind of circuits where the metric of time is involved, it is sequential circuits, and you need a clock signal in that, okay? So what is a clock signal? A clock signal is basically any square wave, okay? So in electronics, since we are dealing with digital signals, we only have two states, right? Either we can go high or we can go low. So a signal that toggles between those, if we have a periodic signal that is toggling between those two states, we can treat it as a clock. And also the duty cycle, which means the on and off period, usually should be equal. Square waves should be there, because we want like the off state and on state to be in symmetric way, okay? So this is clock. You can read a lot about clock and why it is so, like you can read lots of theory about it, but as per me, I think you can just understand while doing it. By doing all the sequential circuits, you will be able to have a good intuition of the clock signal, okay? It's not that much of a big thing. So if we go into sequential circuits, the first of the few elements that we need to cover is flip-flops, okay? Starting off in the sequential circuits, we'll cover today D flip-flop and all kinds of flip-flop, okay, in single video. So I'm not going to waste a lot of videos in flip-flops itself. I'll cover all the flip-flops in this video, and tomorrow, that is the next day, I'm going to cover one of the most important topics in sequential, which is clock division, and that is very important to understand. Okay, so let's discuss about the D flip-flop here. So a D flip-flop basically looks something like this. You must have seen, you have a clock input signal here, the data, doesn't matter what it is, it will be transferred to Q, or if it will be transferred to Q depending on the clock. Okay, so if there is on the rising edge of the clock, it will be transferred to this, and if you have data in these periods, that data will be here only, it won't be reflected here, it will be reflected only after the positive edge of the clock, or negative edge if you have negative edge triggered system setup. So you have these kinds of things. Now during the implementation, I will show you all the kinds of flip-flop. Okay, the JK flip-flop, SR flip-flop, and T flip-flop, and all those things. But practically and realistically speaking, from my experience, it is like those things won't be that much of a big deal. On all you need to know is about the D flip-flop. Okay, D flip-flop is a standard flip-flop that we will be using every time, and that is the more or less the flip-flop that we will talk every time when we say flip-flop. Okay, so D flip-flop is the most important. So let's get into Verilog, and we'll implement this thing on the FPGA. Alright, so here I am on Notepad++. So we'll start writing the code. We need to write the code for D flip-flop, right? So starting off, we'll write module. We'll declare inputs and outputs. So till now, inside the always block, in the sensitivity list, we have written star, right? So star was for anything you write inside this bracket over here. So this bracket basically contains the sensitivity list, all the signals to which the logic is sensitive to. Okay, so if those variables change, this always block will be sort of triggered. Okay, so right now what we need to do is to trigger the always block according to the clock. Okay, so we can basically trigger the always block based on the positive edge or the negative edge. So this over here, if you see, is the positive edge, and this inside here, this is the negative edge. Okay, these are the negative edges, these are the positive edges. So first off, in the D flip-flop, our D flip-flop will be positive edge triggered. So what I need to write is pos edge. Okay, so I'll write pos edge, and the clock variable is CLK. Okay, so write this and begin. And so here this always block will be running, will basically trigger all on the positive edge of the clock. So every positive edge of the clock, what we need to do is we basically need to transfer the D data to the Q output. Okay, what we are going to write here is D, and this is the first difference, this is the second difference over here. As you can see, in the assignment I have written this. Okay, so this is slightly different from this. Okay, so this over here is the inside this always block, we call this thing as blocking assignment. Okay, and this as non-blocking assignment. So why? So the thing is, when you have something like this, so I'll explain you with an example. Let's say we have D is equal to Q1. Okay, and let's say D2 is equal to D. If we write this inside always passage clock, basically this block, what is going to happen is this D will get the value of Q1 first. Okay, so first this will happen, then we get into here, and we will have whatever the D is now will get assigned to D2. But if we write like this, what is going to happen is this is basically non-blocking assignment. So what this will do is basically everywhere this D will be the old value. So this D will not get the value of Q immediately, right? It will take in the next clock edge, what is going to happen, this thing is going to get assigned over here. So this Q will be assigned to D, but in the next clock edge, not right now. Okay, so this will basically act as a D flip-flop over here. It will act same as the D flip-flop. So here in this case, what is going to happen is basically you will, let's say Q1 is 1, okay, and D is currently 0. So in this case, what is going to happen is basically Q1 is 1 and D is currently 0. In the next clock cycle, as soon as this triggers, what is going to happen? D2 is going to have old value of D, because D hasn't changed yet. Okay, this thing will be calculated basically in the same edge, same clock, and these two are not one by one calculated. Okay, this will basically take the old value, and D2 in this case will be 0 and D in this case will be 1 after the clock edge. But if you had simple assignment, blocking assignment like this, what was about to happen was, first D will take the value of Q1, so D will become 1, okay, just like this. But D2 will take the value of D, so this will assign first, then it will go into next step. So basically what is going to happen, now D has changed, it is 1, so D2 will basically be 1. This is the difference between blocking and non-blocking. Okay, so you can also add reset. In fact, I will add reset over here. So what I can do here is, I can have another signal known as RST, and it will be input. So here I will check if reset is pressed. So you can directly write this, or you can write one tick binary 1. Both will do the same thing. If your reset is active low, you will have to write one tick binary 0, but here I am taking active high reset, so I will take if RST and I will do begin. So here what I can do is basically define the output at reset condition, which I will keep 0. So I have also written reset over here. Let's go into the test bench now. So I will write module. So the first step inside the test bench is the instantiation of the duty. So I'll take the duty, which is this, and let's instantiate it over here. So duty name. Since we are testing a sequential circuit, we need to generate a clock. Okay, so since our DUT which is designed under test this T flip-flop, this requires a clock signal, so I need to give this signal to the DUT, right? So for generating this clock signal inside the test bench, what you do is basically write an always block without any conditions. Okay, so you have right now saw that you basically write always at the rate either star or either passage clock and all those things. So when I write unconditional always like this, usually done inside the test bench, we will basically, this runs infinitely. Okay, so this is how you basically generate a clock. You want the clock to be running always. Okay, so what I will do, will write always. Now let's basically have the time scale directive defined. So I'll have tick time scale 1 nanosecond / 1 picosecond. So I have talked about this time scale directive in earlier videos as well. So the first thing is basically 1 nanosecond, which is the unit of time. When we write delay and all, that delay basically takes this unit, and this basically over here 1 picosecond is the precision. Okay, so let's say we are generating a 100 megahertz clock, so you need to basically calculate the time period of the clock. Okay, so when we have 100 megahertz clock, for getting the time, this is frequency, for getting the time period you need 1 upon frequency. So this is 1 over 100 megahertz, so this is 10 to the power 6, and this is 1 upon 10 to the power 8, and will be 10 nanosecond. Okay, this is 10 nanoseconds. Now this 10 nanoseconds is basically the time period of the clock. So from here to here, this entire thing is the time period. So in one time period the clock needs to go high, and it needs to come low as well. Okay, so that is why we will take the half of the time period and we'll toggle the clock according to that. So if your clock is time period is 10 nanosecond, we'll keep the clock as high for 5 nanoseconds, and we'll keep the clock as low for 5 nanoseconds. Okay, so here also what I'm going to write is always, and we'll have delay of 5 nanoseconds. Okay, and then we will define clock is equal to node of clock. So So the clock basically is toggling, right? So whenever you write clock is equal to not of clock, whatever the previous state was, it will get toggled, right? And it is toggling every 5 nanoseconds. So the here if initially if the clock was 1, it will toggle after 5 nanoseconds and will toggle again after 5 nanoseconds. So the time period will become 10 nanoseconds, right? So this is how we generate the clock, and I'll feed the clock over here. And let's get into initial block. Okay, so the initial block, in the initial block we will change the inputs and observe the output from the DUT, right? So we'll go into initial. So since we have a reset, what I am going to do is, for one clock period I will keep the reset high. Okay, so let me wipe all this. What I'm going to do is have the reset signal high for one first one cycle of clock, and then I will keep the reset low forever. Okay, so for that, what I'm going to do, initially I'm going to write reset equal to one tick binary 0, right? Then I'll wait for one clock cycle. So sharp one clock cycle is 10 nanoseconds, and then I'll keep the reset as high, low. So we'll keep the reset as high first, and then we'll keep it as low, since we have an active high reset. Okay, so this will basically create this reset signal, which will initially keep the circuit in reset. So this is how we normally do start a sequential circuit. Okay, we start with reset, and then we go then we toggle the reset low. So initially we keep the circuit in reset so that all the signals basically gain their default values. Okay, this is the technique. So what I'm going to do after reset is deasserted, I will start feeding the signal. So let's start with one tick binary 0. Since it was already 0, it will not change, right? This in this period. Next I will keep it as high after 10 nanoseconds, so we'll keep D as high. Okay, and I'll do it two or three times. Okay, so I've written this basic test bench over here, and okay, inside the initial block you do not do this, since in the initial block you directly assign and wait, so please do not use procedural assignment over here. Okay, so the problem seems to be in the D flip-flop module itself, not in the test bench. So here, as you can see, we have forgotten to do the reg, right? Whenever you do procedural assignment inside an always block, you need to have a reg, right? So here we need to have reg. So before doing that, I actually wanted to show you something else as well. So here in the messages you can see that please check the tickle console output or see FPGA series. Here you can see xvlog.log. So this log file, basically in many of the cases what happens is that you don't really get error messages. I mean, you get the messages, you don't get the details. Okay, so usually what they do is they have all the records of the errors inside the log file. All the processes that are happening are basically stored in the log file, and I'll show you how to check out the log files as well. Okay, so here you just go into this log file location, and for that I've opened it. So this is the log file location, and here you simply open it with the Notepad++, and here you can see that module TFF is ignored due to previous errors. This is the last message that we have seen. Procedural assignment to a non-registered D is not permitted, right? Left hand side should be reg, that we have spotted. So this is usually all the errors will be in a log file. Okay, this is what I wanted to show you. So if you are not seeing some detailed errors, okay, you can go into these log files as well and you can see the errors. Okay, so now we can just fix the error. This is Q equal to D. Okay, in here I actually accidentally did D, so you will have Q is equal to D, a sign like this. Okay, so I fixed it there. Now what we are going to do is we need to do the simulation. So run behavioral simulation. So here you will be able to see what's happening. So what's happening, initially this is the clock. Okay, so this is the clock. So the reset basically unsets over here, and now we have D is equal to 0. Okay, as soon as the rising edge comes, what happens is that whatever the D was in the previous cycle, basically till now, before the rising edge, we get the Q as that. Okay, as you can see, we had D as 0 over here. So now here it after rising edge, it is reflected as 0, and now here data is positive. Okay, data is 1. So here data is 1, so it is not immediately reflected in the Q. As you can see, it will be reflected only after this rising edge. Okay, so as soon as the rising edge hits, the Q basically becomes the previous D, that was 1. Okay, so this is how a D flip-flop works. And as you can see, before the rising edge, this settles down to 0, D settles down to 0, and we have the next Q, which is 0, right? So this is the working of a D flip-flop, as you saw. So I will quickly show you all the other three, which is the T flip-flop, JK flip-flop, and SR flip-flop. Okay, all right, so I've coded SR flip-flop, JK flip-flop, and T flip-flop, and here are the simulation results. So I'll show you. So firstly, SR flip-flop, if you see here, so this up to this here, it is the reset, and after that S is high and R is low. If you can see this region, as soon as the positive edge hits, this output, which is the Q over here, goes high. Okay, now here if you see this one, this is again positive edge, but here both S and R are 0 still. So that means nothing is happening, like we have to retain the previous state. Okay, so in that case, you can see Q is basically the whatever the previous value was, which is 1. Okay, next off, if you see, the R value is high and its reset is high, and so Q should be 0, but here you can see until the next edge is arrived, this is the next edge, it is 1 only. Okay, it basically takes effect after the positive edge. So here you can see this goes to 0. Now in the last state, when basically both are 1, S and R, here you can see the output is 0. Now this is the thing, like in SR flip-flop, both the states, both the S and R cannot be 1. Okay, that is an invalid condition. So usually what they do is, here in the this SR flip-flop code, DUT code, they basically do one tick binary Z to represent that the output is invalid. Okay, but again Z and X and all those things are not synthesizable in our FPGA. So basically we can do 0 or 1, anything, because that does not matter. Like 1 is invalid case, so the result output of 1 doesn't really matter. Okay, so this is the SR flip-flop. Let's take a look at JK flip-flop now. So JK flip-flop basically fixes the last issue, which is 1 Okay, so here you can see again, if we start from the starting, so here reset is up till here, and now if you see, this is the J and this is the K. Okay, so J is held high and K is low here. So until the next positive edge, which is here, in the next positive edge, this basically becomes 1. Okay, and after that, if you see, we have set K is equal to 1 and J is equal to 0, and as soon as the next positive edge comes, since K is 0, output Q is 0. Okay, now the interesting thing here is, when J and K both are 1, in this case SR flip-flop would the output would be invalid. Okay, but here what is happening, it is taking inverted of the previous value. So whenever J and K both are 1, what it does is basically whatever the previous output was, it inverts it and outputs it. This is the characteristic of JK flip-flop. Okay, next off, let's quickly take a look at T flip-flop as well. And here if you see, reset is until here, and as soon as T is high and as soon as we hit the next positive edge, we get output is equal to naught of the previous output. Okay, not Q. Okay, so this is the characteristic of T flip-flop. It toggles whenever the T is 1 at the rising edge. Okay, so here you can see, as soon as rising edge encounters and T is 1, it toggles. As soon as rising edge arrives and T is 1, it toggles back to 0. and here if you see the T input is 0, so toggling is not happening. As soon as it again becomes 1 and in the next positive edge it toggles. So this is the characteristic of T flip-flop. We have basically tested all the flip-flops: T flip-flop, SR flip-flop, JK flip-flop and D flip-flop. Okay, so now what we will do, we'll transfer it on the FPGA. So for transferring for basically implementing all this on FPGA, we need to have the constraint file, right? So I've written the constraint file as well, and I'll show you. If you go into SR flip-flop and if you go into constraints, you can see I've written these constraints. Now writing constraints, till now you already have known everything, how to write constraint and everything. So here I will just explain what I've done. So what I've done is I've taken the clock here. Okay, till now we haven't taken the clock in the constraint. Okay, so whatever your board constraints file are, if you see here, you have clock signal. As you can see, this is the clock signal. Okay, so this clock signal basically depends on your board. Okay, your board can have 50 megahertz clock, can have 100 megahertz clock. In fact, you can change it from here, but basically take this. Usually your board will have 100 megahertz clock. Okay, so this you copy and basically tie your clock to this pin. Okay, here in Nexus board we have the pin E3 assigned as clock. Next off, reset we have set as button, and S and R we have set as switches. Okay, and Q output we have set into an LED. Similarly in the JK flip-flop as well, if you see the constraints, here also we have done the similar thing, just in the place of S and R on the switches we have J and K. In the T flip-flop however, we have one change, that in place of switch we have button. Okay, this one is basically a button. So because single input is there, so button would be good enough, so I've taken button as well here. Okay, I'll show you in implementation everything. We'll test everything in implementation, and in here D flip-flop as well I've written the constraint file, and here you can see it is similar to the T flip-flop. We have taken button here as well. Okay, so here let's put everything on the FPGA. All the flip-flops one by one we will be putting it on the FPGA, and we will notice some interesting thing. Okay, see what is going to happen. Let's just see what is going to happen, and I will explain you while I am basically testing everything. So let's see the implementation. First off, I will upload the T flip-flop code and I'll show you what is going to happen, because I have one interesting thing to show you. So on the constraints I have set up this pin, which is M18. So if I find M18, this one is the pin which is the toggle pin. Okay, so you can imagine the square wave running, and once I press this, the output will start toggling. Okay, and one of these LEDs should toggle. So let's see what happens when I push this. It's toggling, but you can see this weird behavior. Like it's not toggling every time. Like if I push it, you saw it didn't toggle. It basically turned off again. Sometimes it turns on and keeps on, which is the correct behavior, but other times if you see, this sort of behavior is happening. Let me explain you why that is happening. Okay, so as you saw that the circuit of the T flip-flop was not behaving too correctly, and here is the reason why. There are two main reasons of this. So the first reason is that the clock is 100 megahertz, like it is very fast. Okay, so this on the board, when I draw it, I have drawn the zoomed up version, right? Extremely zoomed up version. But on the basically, if I show it on the oscilloscope and anything, it will be very fast. Like 100 megahertz is a very fast clock. Second thing is that the push button that I'm pushing over here, these kinds of push button, they are not definite ones and definite zeros at the time of pushing. What I mean by that is, whenever you push, what happens is that the button sort of bounces, because what is a button? Basically a button has is something like this. You have a contact in here, so basically what is going to happen, you will have one contact right here and one contact right here, right? This is wired to one of the terminals, this is wired to another of the terminals, and when you push the button, it basically comes in contact. But in normal push buttons, what happens is that when you push it, it sort of bounces between the two things before settling. I'll explain this in great detail in next 1 or 2 videos when we are going to see how button debouncing is done. Okay, debouncing the button is one of the most important logics that I mean, it is very basic thing that you have to master in the sequential circuits as well. Okay, like it is one of the things that basically needs to be done in sort of every button scenario. Okay, so that I will greatly discuss in next or next to next video. Next video I think we'll do clock division, and that is also very important, so stay tuned for that as well. Right now what I'm saying is that what should happen whenever you press the button, it should go from 0 to 1, right? This sort of clean thing should happen, but because of the bouncing of the button, what happens is that when you come near this edge, sort of these transitions happen, and then you go to high state. Okay, why these transitions happen? Because physical connections are not ideal, right? Not ideal in the real world. Basically the button sort of loses contact, sort of bounces between the contacts and all, which we will explore again in the next few videos. But for that is one of the reasons. Okay, this push button is one of the reasons. Next reason is the fast clock. Because of the fast clock, this is sampling very fast. So let's see what is going to happen. Let's see, when I push the button, t is equal to 1, but since I'm pushing it using my fingers, my finger is not fast enough to pick the button before the next clock edge, right? Let's say I push the button here, okay, or in fact I push the button over here. So this clock edge arrived, and what happened? Toggling happened. Let's say the input was basically output was basically q is equal to 0, right? Before this edge, and I pressed the toggle button, so t is equal to 1 at this point edge, and therefore the q will toggle and q will become 1. Now I have to lift my finger up before this edge, right? Otherwise what is going to happen? Q is again going to become 0, right? Because t is equal to 1, so q is equal to 0, and the period for 100 megahertz clock is 10 nanosecond. So my fingers obviously won't be able to lift that fast, right? What is going to happen in practical scenario is that this I'm going to take quite a lot of time. So let's say these many times. So t is high for that many times until my hand was on that push button. Okay, until my finger was on that push button. So depending on t is equal to odd or even, the output basically can settle at q is equal to 0 or q is equal to 1, depends on when I lifted my finger, right? So that is one case. Another case is that when I lifted my finger, then also some kind of debouncing thing can happen over here, and you can have this toggling effect. What the value of t was at this point again is sort of like not known, right? So because of the combination of these two effects, we are seeing that anomaly in the output, right? In the toggle flip-flop output. Now how we can solve these? First off, we need to do the debouncing. Okay, second off, for practically observing the Q in the LEDs, you need to slow down the clock. In the next 2 videos, I am going to do all those things. Okay, I'm going to explain slowing the clock division, which is very important. Like one of the most important things in sequential logic is clock division itself. Once you have the intuition for clock division, once you know the basics of clock division, you will be able to do so many things, right? So that is very essential to master, and I'll show you in the next videos, and in next videos as well. I'm going to show you in the next few videos as well. I'm going to show you this button debouncing thing. In fact, I will show you the this transitions on the oscilloscope as well, if it possible. So stay tuned for that as well. So hopefully you understood why this T flip-flop is not behaving the way that we expect it to. Okay, similarly for D flip-flop as well, what is going to happen, since the clock is so fast that my D let's say if I keep it 1, okay, so clock is so fast that LED will be sort of instantly equal to 1, right? Let's say if I put D is equal to 1 over here, Q is equal to 1 over here, because next clock edge basically will the D will be transferred to Q, right? So what is going to happen, this is so fast that it will sort of look like instantaneous. I push D, I get Q is equal to 1. I basically take off my hand from the push button, from D becomes 0, immediately it is going to become 0. So you are not going to see that delay in here. You will not be able to see it. It is happening like that only, whatever the concept of D flip-flop is, it is being followed, but you will not be able to see that time delay, okay? So that also I have basically told you before only. In JK and SR flip-flop also these kind of effects will be shown. So let me show you the next two as well, okay? Let's put the D flip-flop code here on the board, and okay, D flip-flop is on the board, and the input I think is this button again. So when I push, the LED glows, and as I told you, the LED glows instantly, but there is that delay between the next positive edge, okay? But that you can't see because that is too quick. So D is 1, Q is 1, D is 0, Q is 0, but that edge clock I cannot show you practically here because that is happening very fast, okay? I'll slow down the clock and I'll show you in the next videos when I tell you about clock division and everything. But right now you can see D flip-flop is working on the FPGA at least. So let's put the next, which is JK flip-flop and SR flip-flop. So first let's put SR flip-flop. Now it's programmed. Okay, so this is S and this is R, I think. Let me check the constraints. This is S and this is R, right? And okay, so and the LED is again the same. So when I set the flip-flop here, as you can see, set is high, LED becomes high, and when I do set as low, LED remains as high, right? This is SR flip-flop. I have both S and R as 0, so LED should remain in the previous condition only. Next off, when I reset the thing, if I do the reset by taking R is equal to 1, right? This is R is equal to 1, therefore we see the LED in reset condition. Now when I make it 0 again, so S and R both are 0, it retains the last condition, which is basically LED off, right? And again, so this again the clock is very high speed over here, so that is why we are instantly seeing the effect. What is going to happen until the next positive edge comes, this is going to remain in the previous state only, and as soon as the next positive edge is hit, the S is equal to 1 effect will be shown, right? But since here the clock is so fast, the effect is shown immediately, okay? This is SR flip-flop, and again in the SR flip-flop, S is equal to 1 and R is equal to 1 is not valid, okay? In that condition I had told you that we have put 0, and you can put anything, it doesn't matter, okay? In JK flip-flop, however, that 1 condition is valid, and I'll put the JK flip-flop code now, and it is programmed. So now this is J and this is K and that is Q. So the functioning for 1 0 0 1 and 0 0 is same. 0 0 it retains the last state, so if I put it to 1 and if I keep it 0 0, and it retains the 0 like last state, okay? When I put K is equal to 0, K is equal to 1, it basically again goes to reset, right? And when I put it back, K is equal to 0, so what happens is that it retains its last condition. But what is going to happen when I put these two both as 1, it is going to be 1, right? It toggled from the last state to next state. Alright, so we have implemented all the flip-flops on the FPGA and we saw the anomaly which was caused due to higher clock speed, very high clock speeds, and debouncing button bouncing effect, okay? Here I couldn't show you the delay between the signals and the output, okay? Because when I set D is equal to 1 here, there will be some amount of delay before Q will become 1, because the rising edge needs to be basically encountered before D is transferred to Q, right? Here I couldn't show that because the clock was so fast that that rising edge came very fast, right? So that we will see in that video again, in the clock division video. I'll again show you this and I'll show you the proper functioning. So many beginners get confused when these kind of things happen, when they put clock directly, when they put very high speed clock pin directly into their FPGA in their design, and they see these kinds of effect. they basically like get confused what is happening. So this is what is happening, okay, and we will fix this as well. So thank you for watching this video. We will see these effects and we will see much more of the sequential circuits in the coming videos. So stay tuned. Thanks for watching.